Good morning, everyone, and welcome to our quantum computing lecture today. Last week, we started with the architecture chapter, and we started describing bits using our quantum mechanical approach we had so far, but bits are just either 0 or 1. And then we expanded that mechanism to cover qubits, which are like bits, but from a quantum mechanical perspective, which can be in 0 and 1 at the same time, which adds parallelism through the superposition. We saw how we can represent bits and qubits using our approach, and for qubits, we just use the same tools we had before for our quantum mechanics chapter, but this time it's just 2 entries, so it's all much simpler than these more generic states we looked at before. And we also saw that measurements are simpler because there are only two basic states into which our qubit can collapse. So all of the theory we looked at before from a generic perspective are much simpler now. We looked at a few examples, how to normalize qubits, and we looked at various notations that you will see throughout this course, as well as the literature when you prepare your seminar presentation. All of them just mean the same. We also looked at a qubit, which are 8 qubits combined. We saw that we absolutely need quantum computers to actually work with larger quantum systems, because we can only simulate very small quantum systems on a traditional computer, because for larger quantum systems, we just run out of complex numbers that we can store in our memory. And we also saw how we can apply the tensor product to 2 qubits, so that we combine 2 qubits and build a larger state. And we saw again, there are lots of similar notations that all mean exactly the same. We looked at entanglement of 2 qubits and how we can represent this. And then what we wanted to do is we want to build quantum gates. But first of all, we started describing our classical our classical gates with that mechanism. And we used this matrix vector approach we had used before to describe our probabilistic and quantum systems. We had used exactly that to describe our classical gates, like the NOT gate, the AND gate, the OR gate, the NAND gate. And we saw how we can have 2 gates in sequence, and it's all just the same approach over and over, that we multiply our matrices and we have our states represented as column vectors. We looked at more complex circuits, like something like this, and parallel gates, and we saw we can describe all of this actually straightforward using the mechanisms we have learned before. And using that, we looked into reversible gates, so operations we can undo. We can undo a NOT gate, but we are unable to undo an AND gate. And then we introduced a couple of reversible gates, like the C NOT gate, the controlled NOT gate. We looked at its matrix, and we saw the matrix, by the way, is also unitary. And we also saw that the C NOT gate can undo itself, so it's reversible. And then we looked at a more generic one, a more universal one, the Toffoli gate. And we saw with the Toffoli gate, we actually have lots of freedom in describing logic functions. We looked at its matrix, which is unitary, by the way, and we saw how we can customize the Toffoli gate and combine multiple to build larger functions. And we also saw why we need to be able to undo a Toffoli gate sometimes, just to avoid that we had some inputs we didn't want to change because they would be changed. And if we later use this from a quantum perspective, we would create unnecessary superpositions. So we have to undo that. Otherwise, we're just running into more and more challenges when trying to solve the optimization problem we're looking at. Then we saw we can build a NOT gate from the Toffoli gate. We saw we can do a fan out. Fan out here in this context would mean we are copying the input y, and we have it as an output twice. This is something we will get back to very soon in today's lecture. So just remember this fan out here from the Toffoli gate. The Fredkin gate is another universal gate, but we didn't study it in detail. If you wish, just look at it yourself. And now we have all the methodology ready to build quantum gates. Quantum gates will be the fundamental operators we have in a quantum circuit. They need to be reversible. Concretely, they need to be represented by unitary matrices. Some of the gates we had seen before are also quantum gates because they can be represented by unitary matrices. And we introduced new ones like the Harder-Matt gate, which creates superpositions, the Pauli matrices, and a couple of others. And you may need some more of them or some less of them for your seminar presentations, or if needed, you could study the S or T in greater detail. We looked also at the Bloch sphere, which allows us to visualize a qubit. And it's quite helpful to understand what the qubit may look like, as well as we can have an interpretation for some of the gates we have seen before, like the Y operation, where we just flip along the Y-axis. And it's the same for the X and Z Pauli operations. You can study the quantum gates in greater detail if you look into the book. And we finished with the quantum gates last time. Today, we will finish quite quickly this chapter on architecture. There are two more things we need to look at today, and then we'll have some more time to look into quantum algorithms, as well as some of the theoretical foundations of quantum computing. Are you all okay with the content up to here, what we did last time? Maybe thumbs up or thumbs down. So looks good from your responses. Now we just looked at this fan-out gate we built from the Toffoli gate. And this is something that works perfectly fine if you use this for classical values, so just binary values. This will work perfectly fine, but it will not work that way if you have quantum states. Because in quantum mechanics, there is a limitation that is called the no-cloning theorem. And it will have severe impact also on how you build algorithms in the quantum world. Because if you build traditional algorithms, you're used to that you can just copy some variables, like just a float value, or you copy an array or a list or a tree, whatever. And this is one of the most fundamental things we do in a lot of algorithms, that we copy certain values. And this works fine in the classical world, but in quantum algorithms, it doesn't work this way. So there are two limitations, in fact, when we build quantum algorithms. All the operations we want to use must be reversible, because all the operations need to be represented by unitary matrices. And another limitation is the no-cloning theorem. And the no-cloning theorem says that it is impossible to clone an exact quantum state. So you're unable to perfectly copy a quantum state. So you cannot make a copy of an arbitrary quantum state without first destroying the original. And this comes from quantum mechanics, and feel free to read quantum mechanical literature where you can learn more about the no-cloning theorem. But for us, this is just something that we accept in this quantum computing course, because this is not a course but quantum mechanics. So this will lead to limitations when we try to build quantum algorithms, because we cannot just copy-paste some values, at least not perfectly. Big consequence, and like this is one of the reasons that severely complicates building new quantum algorithms, because one of the things we're so used to from classical algorithms is not available. Now, before we saw this Toffoli gate, which allowed us to do the fan out, so we could copy the input. This only works if you use the Toffoli gate, and it's the same for the Fredkin gate. For classical values, it does not work if you put in quantum states. So the fan out we built before is not a violation of our no cloning theorem, because that fan out only works for classical values. So not a violation of what we had done so far. So remember this no cloning theorem, and depending on your seminar presentation, you may come across it or not. Probably many of you will see it again if you read a paper about some algorithm or something, and there's probably something you think that could be done quite easily, but it cannot be done because of the no cloning theorem. The no cloning theorem also has a number of applications in quantum computing. For example, there's quantum key distribution, and quantum key distribution, just in a few sentences. So the abbreviation is QKD, if you see it. It's a protocol by which we have Alice and Bob, and they can agree on a shared secret key, despite they have never met in advance. And contrary to public key cryptography, without relying on any computational intractability assumption. That's what you would typically have in a public key cryptography setting. However, instead, here for quantum key distribution, there's only one real assumption they need, and that's the validity of quantum mechanics and the availability of an authenticated classical channel. Quantum key distribution relies on the no cloning theorem. So I'm not talking here in detail about quantum key distribution, because this is probably a topic that some students pick every year for the seminar presentation. And I think in the last few years, there were always one or two groups that talked about a quantum key distribution. If you're curious how it works exactly, it's described in detail in the book in chapter 5.4, as well as the book published or written by Scott Aronson also covers quantum key distribution in the book and makes a link to the no cloning theorem. So feel free to read this if you want to get a better understanding, or if you're interested in presenting quantum key distribution in your seminar presentation. So this is typically something that the students from cybersecurity are interested in every year, but no matter which program you come from, feel free to look into it. Now, we look at one more thing that we need in quantum computing, and that relates to the foundations of quantum mechanics, and these are so-called mixed states. So far, all the states we have been dealing with throughout this course are something that we would call a pure state. And today, we will also look at so-called mixed states. What is a pure quantum state? Pure here refers to the fact that we can describe our system entirely with, or that the description of the system is entirely quantum mechanical. And the pure state is a state which can be described by a single ket vector as before. So we've always worked with single ket vectors to describe our states. And today we will see so-called mixed states, which come with something on top of that. It's something you can imagine like that on top of our single ket vectors, we put now classical probability theory on top of that. And you could interpret this as asking something like, what if we don't know which quantum state we have? And a so-called mixed state, so it's more like an extension of what we have done so far. A mixed quantum state is an ensemble of pure states, and it's a statistical ensemble of pure states. So if pure states, you have multiple of them, you put probability theory on top, and then you have this ensemble, and you have a so-called mixed quantum state. We'll first do a little bit of theory, what mixed states are exactly and how they work, and then we'll look at why they are relevant to quantum computing. And probably the simplest mixed state you could think about for now is, or one of the simplest ones is, that we have this superposition. We've seen this superposition here in great detail in the last few lectures, especially the last lecture, and we were able to create this superposition through the Harder-Matt gate. And we also have this superposition we created through the Harder-Matt gate. And now you could have both of these states, and for each you have a 50% probability, and you put all of that together, you would have this ensemble of pure states, because this superposition and this superposition, they are pure states, and now we have an ensemble of pure states. I'll switch to my iPad to show you some of the theory. We'll look at a few examples of mixed states, and we see what it's actually useful for in the context of quantum computing. So, as a first note, we need something now that we call the density matrix. And a mixed state cannot be described with just a single ket vector. But we've said a mixed state is an ensemble of probabilities and pure states. And we will introduce now the concept of a density matrix. And the density matrix we can use to describe something like this. So it allows us to describe a mixed state. And oftentimes the density matrix is denoted with a rho. And we can say it's a sum of states, sum of pure states. And we have for each state a probability PS. And what we will calculate now is the outer product of the pure state. So the outer, we've seen largely inner products in this course so far, but today we'll be using the outer product to describe this. So it's psi s, our state, and it's psi s ket multiplied with psi s prime. This here is the outer product. We have the probability PS for this state. And we sum up these products with the sum sign, and that will eventually lead to a density matrix, because this outer product will lead to a matrix. And we have the fraction or the proportion PS for the ensemble in each pure state. And what does this density matrix do? The density matrix encodes all the information that could ever be obtained from some probability distribution over quantum states by first applying a unitary operation and then measuring the state. And this is deeply related to decoherence, as we will later see. But first things first, I've talked about the outer product. We've largely used inner products in this course. So that's just that we are all on the same page what the outer product does exactly. You've all seen the outer product in an introduction to linear algebra, but this time now we work with quantum states. We just do one example of the outer product. And then this should be clear what this blue part is doing. So the outer product, we can say this is psi ket, and psi ket this time is 0 ket plus 1 ket. and we need to normalize this quantum state. We've all seen this before. And what we want to calculate is we have our psi cat times psi bra. That's just what we had seen here before. And that means this time, now we have a concrete value for psi cat. We have 0 cat plus 1 cat divided by the square root of 2. And we want to multiply this with the bra. And you remember for the relation between a cat and a bra, this is something we have seen before, has to do with the dagger, the adjoint operation. And now this is 0 cat plus 1 cat divided by the square root of 2. And we apply, very importantly, the dagger operation. And we can now write this out as vectors. So the first part, so this green part here, this one, and as we've seen before, we can just write this out as a vector. So we have a 1 and a 1. One is for the 0 cat, the other one for the 1 cat, and each entry needs to be normalized because we've divided by the normalizer. And then we have this blue part here. And that's also 1 divided by the square root of 2, 1 divided by the square root of 2, and we need to put the dagger there as well. That means 1 divided by the square root of 2, and 1 divided by the square root of 2. And since in this blue one here, we have these 2 entries, they only have a real component, not an imaginary part. That means all this dagger does is it's transforming this column vector into a row vector. So it's 1 divided by the square root of 2 and 1 divided by the square root of 2. And what I want from you is that you multiply this column vector with this row vector, and you can tell us the result in the chat, what happens if you multiply a column vector with a row vector in this order. It's a different result than if you multiply the row vector from the left and the column vector from the right. Don't forget this. So you can quickly do this, and once you have the result, send it to the chat or turn on your microphone and share this with us. Got the right answer. It's a matrix, a 2 times 2 matrix, and each entry in there is a half. So, worked perfectly fine. This was only the excursus of the outer product that we need in here. And now we'll look at a concrete density. We've just seen this concrete density matrix, or we're building now a concrete density matrix. We've built part of the density matrix here with one outer product. And we'll extend this now. We can say we can have a half probability for the one we have just seen, 0 cat and 1 cat divided by the square root of 2. That means if we say we have this one here, and we take the outer product of its cat with its bra, we would get just the matrix we have done here, and we have a half probability for this one. So this is just the one we have built. So we have the first Sorry, the screen share just stopped. I don't know why. I'll fix it. Sorry about that. So what we have done is the first part here for our first cat multiplied with that product of a half. This is the first part. And the second part is we have a half probability for 0 cat minus 1 cat divided by the square root of 2. And if you say that this is now your cat and you build the outer product with its bra, what this will get you is, and you're free to try this at home on your own, will give you a different matrix. It's 1 half here minus a half, minus a half, and a half. And we also have the product of a half, and we sum them together. And if we sum them together, this will give us the density matrix. And summing this together is perfectly easy. So it's a half here, and a half there, and then 0 and 0. Another question for you is, what does this density matrix, so this is our row from before, what does that get us, or what insight can we get from this density matrix? It in fact follows that no measurement you can ever perform will distinguish this mixture from a half probability of 0 cat and a half probability of 1 cat. If you're curious to learn more about density matrices and mixed states, there's a lot of that in the book. There are applications of mixed states throughout this course and also for your seminar presentation. And for this, I'll switch back to the slides. So just well formatted, this is what we had just done as examples. And the density or density matrices can describe also pure states. So it's the same approach to describe mixed states as well as pure states. Feel free to look at more examples in the book if you wish. And the density matrix can also be interpreted as a way of using the one-particle formalism to describe the behavior of many similar particles by giving a probability distribution, or thus an ensemble of states that these particles can be found in. And mixed states arise in quantum mechanics in different situations. It could happen when the preparation of the system is not fully known, and you must deal with a statistical ensemble of possible preparations. You could also be dealing with mixed states when you want to describe a physical system which is entangled with another one, and its state cannot be described by a pure state. Mixed states are also relevant in quantum computing in relation to decoherence. So decoherence is something I had talked about a little bit, Horst had talked a little bit about, and next week in Horst's lecture, he'll provide a little bit more insights into decoherence when we look at concrete quantum computers. When you deal with decoherence, we've mentioned this before, decoherence means that your quantum system is not perfectly isolated from the world around or with other systems, including, for example, the apparatus for measurement. And then your quantum system starts to decohere. And density matrices are one approach to describe that your quantum state starts to decohere and thus actually loses its pureness. You'll see a little bit more about decoherence in next week's lecture of Horst. Theoretically, at least from a theoretical perspective, decoherence could also be undone because it could be described eventually just as an operation, but in practice you're unable to undo the decoherence because these systems and their interactions are just too complex. And decoherence is a real limitation in quantum computing because your system starts to interact with the environment, loses its pureness, and the more operations you have running in your quantum circuit means the more and more purity you're losing in your state or in your system. And that's not great at all. Plus, you have the measurement on top, which also adds uncertainty. We can look at another example from quantum communication, and there are, in fact, a lot of practical scenarios in which the state of our qubits cannot be written down, as we've always done before, as a linear combination in a given basis, but instead we have to express all of this in terms of ensembles, which are statistical mixtures of the pure states we have seen before. Imagine the following scenario in quantum communication. Alice wants to send to Bob a state that we call plus ket. But we have noise in our communication channel, so there's a certain chance that our state could flip from plus ket to minus ket due to noise in the communication channel. And there's a certain probability, P, that this could appear. So there's a probability that Alice sends to Bob the right state, or that Bob receives the right one, the plus ket, and that probability would be 1 minus P, because it either flips or it doesn't flip. And for flipping, we have the probability P. For not flipping, 1 minus P. So Bob's state is either plus or minus ket, but not a superposition of the two, because it either flips or not. And we want to know, if we want to know what will happen to Bob's qubit after, so Bob receives this, either plus or minus, and he applies then some other gates and performs a measurement. And when we want to know what will happen to the qubit after receiving and applying these gates, we have to consider both of these cases separately. And we could look at them separately, but this could be actually quite a difficult task when you deal with more than two states, because it could be far more possible states in a larger system. And here the beauty is all of this can be described super easily with the density matrix. So you don't need to track individually all these different scenarios. Rather, the density matrix allows you to do this. And there's a great example with Qiskit. So Qiskit is a library from IBM for quantum computing. Next week, there will also be a lab problem after Horst's lecture in which you will use Qiskit. You'll be able to run some of these operations on a real quantum computer. And if you're curious about the example I just mentioned about the density matrix, there's also a code example with Qiskit in which you can run an experiment like this. Here's a link to that one in case you want to follow up and learn more about mixed states. So we are almost done with this architecture chapter. I know it was a lot of theory we did in the last few weeks, and there's a very helpful website that is called, or its URL is called quantum.country. Has any of you ever come across quantum.country? If you have ever opened this website before, maybe thumbs up or thumbs down. I'll show you now what it's all about and why this is, from my perspective, so helpful. Maybe send me a thumbs up or thumbs down whether you have come across this or not. Only negative responses, that's fine. So if you open quantum.country, you will come across different essays. There is an essay which is the introductory one. It's called Quantum Computing for the Very Curious. If you scroll down here, there's lots of text. And if you want to understand or get a different view on the concepts we had discussed so far in this course, or just a revision, take a look at this text. It takes a little bit to read it, but I think overall it's well written and can give you some good insights. But the idea of quantum computing. There are some maths in it. We have done far more maths in this course, but probably you still see the essence. And in here, there are questions that you need to answer. So the question was, how many dimensions does the state space of a qubit have? And I already clicked on it. We said we remembered it. Now the question is, the state of a qubit is a two-dimensional V what? It's a vector. We remembered it. What are the three types of physical system which could potentially be used to store a qubit? We had looked at that in the course before. Electrons, photons, atoms. Say, now you didn't remember this. And it's perfectly fine if you forgot this. And what you see down here is you should be opening or doing this essay multiple times in the next few weeks or next few months. And each time you will do these exercises, but the system will also remember what you passed and what you didn't pass, and it will preferably show you those that you had failed before, and you can get a better revision, and over time you will remember this ideally forever. You can scroll down. In order for this to work, you need to sign in with your email or your Google account, or it's your choice whether you do it, whether you sign in or not. But this will certainly help to run all of this and store it, or if you access it from a different computer. And what we see here is we have qubits like 0 ket and 1 ket. They are defined here. And there are a few constraints about the qubits we had learned, and there are more qubits. And next part is, what does the state mean? Why is it a vector in a complex vector space? We had seen before, we want to generalize probability theory, and for this, we need complex numbers. In here, you find some other explanations for this. You see various gates like the NOT gate and so forth. So feel free to read this essay. We've also seen the C-NOT gate. So there's lots of stuff you will see here you have seen before, maybe a few small notes that are new here and there. But overall, this should be a very good revision of what we have done throughout this course, because now you have the weekend. So you should ideally read this whole essay just to have a very good revision and maybe a few small new insights. I used this years ago, found it very helpful, and there are in fact more essays. There is an essay about quantum mechanics distilled. It's the last essay, because we've not just looked at qubits, we've also looked a little bit more quantum mechanics throughout this course, and feel free to read that essay as well. It will provide you probably with a very good revision as well, what we have done in here. And this figure here is overall super helpful. quantum mechanics in a nutshell, which are states and dynamics. We've looked in detail into states and dynamics. We didn't talk too much about measurements because I said measurements are only interesting or needed for us to measure either a 0 or a 1, but this can be more generalized. It's something that we skipped in the slides, and I told you if you want to learn more about this, take a look in the book. This is highly generalized, not just for qubits, and we've looked into combining systems for which we use the tensor product, something we've also done in detail. So if you want to have a very good revision of quantum mechanics, also take a look at this essay. So you can also read content written by someone different and may get here and there a few new insights or different interpretations of what we have done. There are two more essays. One is the quantum teleportation. It's a relatively short one. It's something we're not looking at in this course. If you want to learn about the quantum teleportation, take a look in this essay. And there is one that is on the quantum search. And that's the Grover algorithm, because now in the next chapter, we will look a little bit into selected quantum algorithms. And one essay that describes in detail the Grover algorithm is provided in here. You have all the tools available to read this essay in detail if you wish. So I think overall these 4 essays, or at least these 3 ones, the quantum teleportation isn't maybe that important for this course, but still feel free to read it if you wish. Now that we have finished the architecture, we have a couple of smaller chapters left. So the roadmap is today we will look at selected algorithms and theoretical computer science. Next week, Horst will will provide a few more insights on quantum computers and programming. There'll be a lab problem, and we'll come to applications and eventually the topics of your seminar presentations. Today we will look at a few quantum algorithms. We discuss all of them briefly because every year some students pick some of these algorithms for an in-detail discussion through their seminar presentation. But for each of these algorithms, I'll briefly want to show you what they are about and why they are important, as well as some insights into their complexity. But first, we can wonder how many quantum algorithms are there? There's a very interesting website that was also created by Scott Aronson. So we come across Scott Aronson's works a few times in this course. And the website is called the Quantum Algorithm Zoo. And I will do another screen share so we can briefly look at it together. So the Quantum Algorithm Zoo is, Scott Aronson claims, a comprehensive list of quantum algorithms that have been published. Sorry, this was not by Scott Aronson, actually someone else, so I was mistaken. I'm sorry about this. It's by Stephen Jordan. And it's a collection of quantum algorithms that have been published throughout the literature. You can look at them. It's a few dozens of algorithms. For example, quantum approximate optimization comes with a super polynomial speedup. There are some implementations and some references. There are other algorithms like quantum dynamic programming. Comes with a polynomial speedup. And you get a quick summary what was proposed in the literature and what the computational impact of that algorithm could be. Some of these algorithms here could be interesting again as a seminar topic, but it turns out that a lot of these algorithms that have been proposed are largely from a theoretical perspective. And there are not that many that have a lot of real-world applications, at least probably not in the foreseeable future. Yet they could be interesting for further study if you wish. And it's probably the most comprehensive collection you can find on the internet, and that's why I put it in here. Now we can wonder how many are actually that useful. And it turns out that there are not that many that are actually useful. And we'll look at some of them, and we look at also some of the first ones that have been proposed in the literature. And then there are dozens more in case you want to study this for your seminar presentation. But a lot of quantum algorithms have pretty much the same structure, and they have a lot in common. So we need to access our quantum computer from outside, from the classical world. That means we need to put into our quantum computer classical states. So the system will start, or the quantum algorithm will start with classical inputs. Now we want to take advantage of quantum effects. So the first step should be that we create a superposition of many states, because then we have a parallelization and can take advantage of that. Do you still remember which gate creates superpositions? Just a quick revision. If you remember the name, just send it here in the chat. I'll see who responds first and wins this challenge. So if you still remember the gate that creates a superposition, send it to the chat. I'll see if anyone is actually remembering this on a Friday morning. Got the right answer. It's the Harder-Matt gate. So Harder-Matt gates would be very much at the beginning of our quantum algorithm. Then we will do some operations to work on that superposition. And all these operations need to be unitary. And we've seen a few gates so far that we could be using. Eventually, we have finished, and we need to transform these quantum states into our classical ones, because outside the quantum computer, we can only deal with classical values. That means we need a measurement. We've discussed all of these steps so far. We've seen in this course how we can create a superposition. We have seen measurements, and we have seen various operations. Obviously, there are some variations of this, but nonetheless, this is some general scheme that probably applies in this form or a related form to most quantum algorithms. But also as a summary, there are challenges, because measurement is not deterministic. We've seen this. So you run the same experiment twice, you may get different outputs. This is partially caused by the measurement, but also by decoherence. Decoherence is a major issue in today's quantum computers. And that's why you would have to run the experiment multiple times, not just because of the uncertainty in the measurement, but also the uncertainty created by decoherence. The hope is in the future that quantum computers could handle decoherence, for example, by using error correcting codes. There's lots of research on this at the moment, or totally different architectures, but at least today, decoherence is a reality. Quantum computing was proposed initially by Feynman in the 1980s or so, and one of the early pioneers in that time to look into quantum algorithm was Mr. Deutsch, and he named an algorithm after himself, the Deutsch algorithm. And it's absolutely a toy algorithm, as well as the extension we will see next. And you have a function with an input that is either 0 or 1, and the output is either 0 or 1. And now we can map the 0 to 0 or 1, and the 1 to 0 and 1. So we have 4 possible functions. For example, we could have the 0 and 1 both mapped to a 0. We could have the 0 mapped to a 0, the 1 to a 1, the 0 mapped to 1, or 1 to the 0, or both inputs mapped to a 1. So we can write this out. A function with input 0 or 1 is mapped to 0 or 1. And we can say that a function is balanced or constant. Constant would mean that f of 0 is the same as f of 1. So f of 0 is 0 and f of 1 is 0. So this one here would be constant. The last possible function is constant as well, where f of 0 is 1 and f of 1 is 1. But a function can also be balanced if f of 0 is different to f of 1. So f of 0 is 0 and f of 1 is 1, or just flipped here. And now we have a function and we want to know, is it balanced or constant? And this problem was described in 1958, and it showed that quantum computers could solve this problem here faster than classical computers. It's an absolutely toy problem with a super simple input and a super simple output, but at least it was shown that quantum computers could provide a speed up here. At that time, quantum computers did not exist. They were purely a proposed concept, so it was purely hypothetical at that time. A few years later, a generalization of this Deutsch algorithm was proposed, the Deutsch-Jozsa algorithm. And this time, the input is not just a 0 or 1, but in fact, a string of n zeros and ones. So that's why we say an input of 0 and 1, n many inputs. And that string will be mapped either to 0 or 1. And what we want to know in this context, if a function is balanced or constant, and balanced here would mean that exactly half of the inputs go to 0 and the other half of the inputs goes to 1. Or we want to know, or the function could be constant if all the inputs go to 0 or all the inputs go to 1. And now we want to know if a function is balanced or constant, and in classical computing, this would need O of 2 to the n much time. That's exponentially growing problem because n gets larger, and then the computing time you would need to determine if a function is balanced or constant would go up exponentially. The Deutsch-Jozsa algorithm can solve this problem, however, with an exponential speedup. And this was one of the first algorithms shown where quantum computers can lead to a massive, so an exponential speedup. From my perspective, this input and output is still a toy problem, probably with very limited real-world use cases, but it showed you can have a quantum algorithm that provides an exponential speedup. There's a related algorithm as a toy problem. It's the Simon's algorithm. And these algorithms, if you want to know how they work, they're explained in great detail in the book. I don't discuss them here in super great detail because the second half of the course is a seminar. So some of you may be picking the Deutsch-Jozsa, or Simon's algorithm. If there is someone presenting the Deutsch algorithm, and if there's someone presenting Deutsch-Jozsa algorithm, I would make sure that the group presenting Deutsch comes first, and then Deutsch-Jozsa, so you can build on top of each other. Take a look in the book. It's a couple of pages per algorithm, and it's certainly something you could study and present during the seminar presentations, or the Simon's algorithm, which is another toy algorithm. But they're all toy algorithms or toy problems. We'll now look at two algorithms that are actually far more interesting from a real world perspective. When we started this course a month ago, we looked at the black box search problem. And that was the very, very first few slides of the course as a motivation. And the problem that we are dealing with, we have a black box function, and that one produces a particular output. And we want to know which of the n many inputs, exactly which of that input produces that output that we want. So which input is actually the one we are looking for to get that output. And this is the black box search because we don't know the structure of this black box function. We cannot do any sorting. It could be more than just integers. It could be totally different objects. So we are unable to optimize for this in traditional computing. So the worst case in traditional computing is O of n. Obviously, the best case is O of 1 if we just try 1 and it turns out to be the secret we're looking for. So the first one we put in produces the output we wanted, so we were just lucky. But this best case is possible yet unlikely. Worst case is O of n, and the average case is O of n half. But O of n half, you remember the constant factors disappear, so O of n half is still O of n. And with the Grover algorithm, we can get a squared speed up solving this. And the Grover algorithm will find with a high probability the solution in about pi divided by 4 times square root of n many iterations. So constant factors disappear, pi and 4. That means this is O of n. We're dealing with a non-deterministic algorithm. So the solution we get from that algorithm may not be necessarily correct because we have decoherence, we have measurements. All of this contributes to the uncertainty. But once the Grover algorithm returns a solution, we can just put it into the black box function and we see if this is actually the solution, if for that input the black box function returns the output we are looking for or not. If it does, we have found a solution. If it doesn't provide the output that we are looking for, we have to run the black box search again. And because of all of this uncertainty, we may be getting a different result. And if we get a different result, we will put that one into the black box function as well. And if it produces the output we wanted, we're fine. If it doesn't do, we repeat this. But typically, you would just need a few instances to run to actually get the solution we are looking for. And we don't really care about the distribution of solutions because we just care about the right solution here. And maybe it works with the first attempt. If it doesn't work, we have to try it a few more times. But each time running this, it's O of square root of n, and then you could say maybe 5 times O of square root of n. It's just a constant factor disappearing. So you don't need to try this usually thousands of times, but just a few times. At least this is the belief. And when we have larger quantum computers available, we'll see how it eventually materializes. The Grover algorithm is helpful. It provides a squared speedup. The Grover algorithm is also helpful because it's a highly generic algorithm. I could use this for optimization of machine learning models. I could be using this for all sorts of other search problems. So it can be applied to lots of different problems. It provides a squared speedup, which is already enormous, but far less than exponential. So we wish to see there was something that could provide an exponential speedup with a quantum computer. That's the next algorithm we'll look at. However, if you want to study this in the Grover algorithm in greater detail, it's just the essay I mentioned a few minutes ago. It's the essay on how the quantum search algorithm works. Feel free to take a look at it. It discusses the Grover algorithm quite well with a few small simplifications, but overall it should be still okay for a first insight. And you look at the essay, you can probably read it in half an hour to an hour, including doing some of the revisions. Certainly doable and could be a good basis for a seminar presentation. For the last algorithm, we are interested in exponential speedups. So this is what I just mentioned. And this is where the Shor's algorithm comes into play. So our goal is we have an integer n, and we want to do an integer factorization of n. So we want to know p and q which make the product, which is then n, and p and q are prime numbers. How can you solve this problem? With classical computing, there are lots of improvements have been proposed for classical computing. What is typically used is a general number field sieve, and that runs in this complexity here. This is slightly below exponential, so it runs in sub-exponential time, yet it's extremely time-consuming. And that's why today's encryption cannot easily be broken, because the integer factorization is computationally tough to crack. Shor's algorithm was proposed decades ago, and in fact it runs in polynomial time. This gives us an almost exponential speedup compared to this general number field sieve, and obviously an exponential speedup to very naive ways how to solve this. And the complexity of Shor's algorithm can be written as something like this that I'm not going to be reading out now. So it will be massively faster. And once this becomes a reality by having larger quantum computers with far more qubits available, with low decoherence, this could mean the end of today's encryption. And that's why IT companies are working massively on new encryption methods that are quantum safe. It's something I also mentioned at the beginning of the course, in which I said that NIST, so the National Institute of Standards and Technologies, has just published a few algorithms that are quantum safe, at least after massive reviewing, and now they need to be implemented by IT vendors. And slowly over the next few years, encryption needs to be converted from classical to quantum safe. And then once larger quantum computers are available, encryption is still safe. It's unclear how long it will take to have such larger quantum computers that work reliably. This is something that Horst will mention next week a little bit. It's unlikely that this would happen in the next few years. So it looks more it would possibly take longer. So that's why there's now enough time for doing that transition to quantum safe encryption the next few years by larger IT vendors or providers. Google has massively worked on this kind of stuff. And then will probably be safe once larger quantum computers are available. And it's unlikely that they would appear anytime super soon, and it's unknown when they could appear. Some people claim they would never appear, something I disagree with. But probably still further away, so there's enough time to do that transition. Now we have looked at these algorithms, and in fact, we can assess now each of these algorithms and find four important properties. The first property is called performance. It has nothing to do with speed. Here, performance means that the algorithm solves a task well. So we have a concrete problem and we want to solve it well. That's performance. Faster means speed up. So the algorithm runs faster than classical competitors. Relevance means the algorithm solves a problem that is actually relevant, for which there are real-world use cases, so something concrete. And availability would mean the technology to implement the algorithm has a reasonable chance to be available soon. Now we have these four algorithms and we can assess them together. The Deutsch algorithm does not, so this was just if a simple 0-1 function is constant or balanced, we get a minor speed up. The Deutsch algorithm solves this problem well, could be done on a simple quantum computer, but it's absolutely not relevant, as there are probably no real-world applications for this. The Deutsch-Jozsa algorithm is the one where we have n many zeros and ones in the input, and we want to know if it's constant or balanced. The Deutsch-Jozsa algorithm solves this task well. It comes even with a massive speed up, probably not relevant for the real world, and for small n's could be done on a small quantum computer in the future. And the larger n, the larger the quantum computer you would need. But both of them are not really relevant. The Grover algorithm, however, solves the black box search quite well, comes with a squared speedup, and solves absolutely a real world problem. But we don't know when quantum computers are available that are large enough to run Grover's algorithm on a substantial input size of the black box function. Could be happening in a few years, could be decades away. There's lots of uncertainty about this. And it's the same with Shor's algorithm. It solves the problem well, comes even with a near exponential speedup, solves a real world problem, focused on integer factorization, while Grover's algorithm is more generic, but it's also unlikely when this would be available on real hardware. And I'm unable to look into the future for the next 30 or 40 years, but you're about to finish your degree in the next few months or next 1 or 2 years, and you'll be out working for 40 or 45 years, whatever. And obviously, we expect there will be a lot of developments around quantum computing, and this is what this course is meant for, that you're prepared for this quantum future. And as new developments come in, you can follow them and you can see what is actually happening out there. And we'll be seeing when Grovers and Shors will become a reality when we have quantum computers available that are large enough. So this is my assessment of these four algorithms. Obviously, we could balance this and say maybe Grover's algorithm is super relevant because it's generic, while Shor's is relevant but tied to one problem. But I just put either one tick or zero ticks, not like multiple to weigh this, but you could put multiple ticks to weigh them if you wish. There are lots of selected algorithms that you could be presenting in your seminar if you wish. And we'll now come to the theoretical computer science chapter for today. And we'll be talking about the limits of quantum computing. We'll look at complexity classes. And since there is an essay that prepares this super well, which is this one here from Scott Aronson, I didn't have to create lots of slides on this because it is explained so well in this essay. And I want to know from you who has read the essay, The Limits of Quantum Computing, The Limits of Quantum. I had asked you last week to look into it. Maybe just raise your hand or thumbs up if you have read it, or thumbs down if you have not read it. So one student has read it, so that's good. Maybe you want to turn on your microphone and tell us a little bit if you liked the essay, what insights you got from it, if there was anything you disagree with or something you didn't like, or what was your impression from reading it? Let us know.
So I've got several theoretical problems with this quantum physics, so I'm got troubles to I can follow somehow, but so this essay was for me quite hard to grasp. I think if you're more into this complete theme of the quantum physics, quantum computing, it's very interesting. It's good explained. I liked it. It helped me to grasp a few things I didn't realize how they work by now totally. So it helped me. I think it's good.
All right. So no one else raised his or her hand. So thanks for your insights. So if you haven't read it yet, you should really read it on the weekend because so I like this essay a lot because there's a lot of misconceptions on quantum computing on the internet and the newspapers. You would hear like super smart computers that would end all of traditional computing, and it isn't that. Um, this essay is from 2008, so it's been 16 and a half years since then, but it's all about a theory. So this doesn't change. The theory is settled. Obviously, in that time, there were no quantum computers really available yet. This has changed over the last 16 years, but the theory stays exactly the same. So the one who read it, in which degree program are you? Maybe so I'll ask you another question. Tell us which degree you're studying, since this course is open to everyone.
Master's degree in computer science.
Okay. So for the one studying computer science, there were a couple of things in here that you have definitely seen in your undergrad in an introduction to computer science, like so-called NP complete problems, which are certain computational classes we will look at now. I will not read out this essay, but I'll just tell you the key essence of it and why I personally like it. I think it makes the topic of quantum computing available to a larger audience, goes back to some of the history, and then it looks into computational problems. There's a quick quantum computing 101, maybe as an executive summary of what our whole course is about. You can probably get it from here. And then since this course is highly interdisciplinary, we also have students from business and engineering. To those, there are probably quite a few new terms in here. There is a class called P. It's a set of computational problems that can be solved in polynomial time. So polynomial time would be O of n squared, even O of n to the 1000, even though such complexity classes are unlikely and probably super slow to solve the problem. This would be all polynomial. But most real world problems in P are something like O of n squared, O of n to the third, O of n to the 1000 is probably rather unlikely. Then you have a set of a class of problems that is called NP. And NP does not mean not polynomial. So it does not mean that some people sometimes think NP stands for not polynomial. In fact, it means non-deterministic polynomial time. And problems in NP are harder to solve, but you can verify the solution in polynomial time. So once you have a solution, you can relatively easy verify whether the solution is correct or not in polynomial time. But finding the solution is tougher. And then there are so-called NP complete problems, and they are in essence the hardest of the NP problems. And for these NP complete problems, if you were ever able to find an efficient algorithm for one of them, then that could be applied to all the NP completes problems as well. And now there is one unsolved problem in computer science, and that problem is the question whether P is the same as NP. And we can try to visualize this. And this is visualized down here. And that's one of the reasons why I like this essay a lot. So we have the problem, or we have P, which is the set of problems we can solve in polynomial time. Then NP is here in orange, the ones which are harder to solve, but we can verify the solution in polynomial time. And we have these NP complete problems, which are the hardest ones. And if one of them could be solved efficiently, then all of them in NP could be solved efficiently. The big question in computer science is whether P is the same as NP. This is unsolved. There have been lots of attempts to prove whether these two classes are the same or whether they are different, but none of these proofs has been accepted as correct. To me, I personally would favor that P and NP are different classes. So NP, there would be problems that we could not solve efficiently in polynomial time. This is, I think, what the majority of computer scientists believes, but there's no proof yet to show this. And there's even a website on the internet of people who have attempted to prove whether NP and P are the same or not, but none of these proofs has been accepted as correct. I once met a person, he was very convinced that P and NP are the same, and he tried to publish a paper on this, but it didn't get accepted. I think the paper had some fundamental flaws, but he still believes that P and NP are actually the same. I would say, at least in my network, the majority of people believe that P and NP are different. Now, where does quantum computing come into play? The class is called BQP. And BQP are algorithm or are computational problems that could be solved efficiently by a quantum computer, which includes the set or class P. Problems we can solve efficiently with a traditional computer would then also be, you would be able to solve efficiently with a quantum computer. This doesn't mean that a quantum computer is always faster than traditional computers. There could be some problems that run super fast on a traditional computer, but maybe 100 times slower on a quantum computer, which is maybe not optimized for a specific problem. But BQP includes more than P, and it's this area around here. And these are problems that cannot be solved efficiently by a traditional computer, but by a quantum computer. For example, factoring. So we've seen this Shor's algorithm. It addresses the problem of integer factorization, it's in NP, and we believe that NP and P are different. So we could solve this efficiently. There are some other ones, like other algorithms, for example, the discrete logarithm is also something mentioned in the quantum algorithm. So BQP includes these things we have studied today. Grover's algorithm, Shor's algorithm, Deutsch-Jozsa, and so forth. So BQP appears bigger than P, but not every problem from NP falls into BQP, and the NP complete problems don't fall into BQP. This figure is super interesting because it shows that quantum computers are not like supercomputers that would, replace all traditional computing and suddenly solve every computational problem substantially better. It isn't that. And this figure shows it well. However, this all relies on one assumption, that P and NP are different. If it were shown that P and NP are in fact the same, probably this would eliminate the need for quantum computers altogether. But even if it was shown that P and NP are the same, you would still need to be able to find efficient algorithms to do this. It doesn't mean that someone just shows that P and NP were the same and all of this would be easily solved. You could only do this for NP complete if someone found a solution to one NP complete problem that is efficiently, then that solution could probably be easily applied to all the other problems in NP complete. But if P and NP were shown to be the same, then probably NP complete would also collapse, and probably the need for quantum computers altogether. Yet, from my perspective, it is highly unlikely that P and NP are the same. Most likely they are different, so there's still a need for quantum computers. So this is probably the essence of some of the most important foundations from theoretical computer science. I think the essay here explains this quite well. If you read it for the first time, probably you need to read it multiple times if you have not come across this in a computer science undergrad program. But this course is highly interdisciplinary. And the essay also would assume that P and NP are different. And that's where this whole figure relies on. There is also some examples of what a classical computer can do and what it cannot do efficiently. So the P problems we've looked at, the NP problems, the NP complete problems, just with a few more examples and a few more sentences. Then the essay addresses black boxes, so black box search, and introduces the black box search, the Grover algorithm, and there is the question whether there could be something beyond quantum computing, some super exotic physics, but this is highly speculative, and such computers, if they existed, they would defy the known laws of physics. So this is purely, I think, as of here, purely speculative and super unlikely, but it looks beyond for maybe some new thoughts if you wish. So maybe the last 2 pages of the essay aren't that important, probably highly speculative, but it's still good to have some outlook and maybe look beyond the limits of what is possible today. But the first 6 pages are probably the most important ones, up to here, or probably up to here. So my hope is you'd be reading this essay for your homework this weekend and get some new insights. And probably if you read this essay, this will help you also to understand some of the goals of this course better. That's why I put it here. There are more classes. So the classes we've looked at, the ones that are most relevant, P, NP, NP complete, and BQP, the ones that could be solved efficiently by a quantum computer. If you take a look in our course book, Quantum Computing for Computer Scientists, Chapter 8 is also devoted to theoretical computer science. And in fact, it covers NP and P, BQP, but some other complexity classes as well. I have read that chapter a few years ago. It's probably quite tough to read unless you have a very good understanding of theoretical computer science. So for the curious among you, feel free to read chapter 8 in the course book if you want to understand more details of these complexity classes, as well as some new ones like BPP, ZPP, RP. I read it a few years ago, got some good insights, but this is definitely beyond the course because probably the whole chapter 8 could be a separate course in itself for a whole term. So please focus on the limits of quantum. And if you have understood this and you're curious, feel free to read chapter 8 in the book. We're done with today's lecture. Next week, Horst will talk again a bit about quantum computers and programming. Next week, there will be also a lab problem. And next week, I'll also say more about the seminar presentations. And if you've seen iLearn, I had also sent you an update about the deadlines concerning the seminar presentations. But I'll say this next week again, and then we're all on the same page. If there are any questions, let me know. Otherwise, if you're okay, maybe just send me a thumbs up. or maybe some red sticker if I shall wait for you, with there only being positive reactions. I wish you a good weekend, and I'll see you next week for the next lecture. Take care and bye bye.